today I would like to give you an overview of why we do field collective robotics, why I'm interested in particular. I come from the space domain. I was working for the European Space Agency before becoming professor, and I was an embedded systems engineer. That's why you see in the word cloud, there was a lot of design space exploration, real-time, embedded systems. Fundamentally was working in radiation effects on electronic systems. And I moved into robotics. It was something that I always loved. About 10 years ago. And then I started working on it, and then it snowballed, and now I mostly work in robotics. I still do some embedded systems on the side. So first thing I want to show you is that why I'm interested in field collective robotics. This you see here is one of the rovers that is currently on Mars. Remember that I come from the space domain, and this is clearly CG. It's not, nobody was there filming this. But this rover was landed on Mars in 2021, and it cost about 2.7 billion. And it is a sizable rover. It's like a small car, and the only capabilities that it has is a waypoint autonomy. So it has a powerful onboard computer for space, but it's not as powerful as anything you see normally. And despite being this expensive, it moves rather slowly on the surface of Mars. And if we want to explore a planetary surface in any reasonable time, we can't rely only on the robots like this. And the reason is that just it takes such a long time. If you look at the timeline of robots in space and how many kilometers they did, we have the crown goes to Opportunity. Opportunity was one of the small robots that was sent in 2004. And after more than 10 years on Mars, managed to drive about 45 kilometers, which is nothing if you compare to the size of Mars. Curiosity, 32 kilometers, Perseverance, 28. You see that the robots or the vehicles that did the most kilometers were actually piloted by humans with the Lunokhod 2 with 39 kilometers on the moon. So if we want to do any form of exploration, you can't just rely on one robot, because in one day, there's only so much you can do, so much you can see. And that's why we had Ingenuity. We had the first multi-robot system deployed in space, where we had a rover and a helicopter on Mars working together to explore the environment. And if you add more robots, you can multiply the amount of terrain, the amount of exploration you can do. That is why I'm interested in multi-robot systems for space exploration. Our target mission is exploring caves on Mars, on the moon, with a group of robots as fast as we can, because we don't have sunlight. The environment is very cold, so you need to be very quick in your exploration and collecting the data. So with this application in mind, my lab is working on fundamentally everything that you can possibly think of to make this application a reality. One other thing you have to consider is that autonomy is absolutely essential. This is why we had the Lunokhod was one of the main drivers of kilometers on the moon, because it was piloted by humans. The idea is that if you go to the moon, you have 400,000 kilometers of distance, which gives you about 2.6 seconds of round-trip communication. I don't know if you ever tried to pilot something, remote control something, with a 3-second latency, 2-second latency. It's extremely difficult. I used to do experiments with children. I go to schools, and they always ask me, why don't we pilot, robots, with like we do for drones? And then I make them try. I say, okay, try this robot. We added a delay of 2 seconds. Stop the robot at that line. They overshoot, they undershoot. It's really hard to do. Basically, it becomes very difficult to do any form of teleoperation with a latency above half a second. And if you have a robot on Mars, well, then you have 20 minutes of communication latency, which makes it fundamentally impossible. You need to rely on autonomous systems. So putting this all together, the main motivation I have is to have multi-robot system exploration as autonomous as possible that provides information to an operator on the moon or on the Earth or on the lunar gateway, wherever it is. Yeah. And there's also another thing, if you have failures, you need to be able to recover from failures. This is a classic example of a robot failing and rolling down the mountain. So what do you do in this case? You have the robot is failing, is rolling down, and you're 20 minutes away. You won't know what happened until you are until 20 minutes later. So the robot has to be able to recover by itself. So to achieve this, we try to intersect what we do with inspiration from nature. So I'm sure that people, you guys here are familiar with the concept of swarm intelligence. The idea is that this is a phenomenon where you have multiple agents that are rather simple, but when they put together, they have a behavior that is basically greater than the sum of its parts. And we have lots of examples in nature with flocks of birds, schools of fish, swarms of bees, ants, etc. And the interesting thing is that if you look at nature, we notice there are very interesting properties. The behaviors are very efficient, so they require little energy. They are generally well adapted to perform their tasks. They are very robust. If you ever had ants in your house, it's very easy to see that they are very robust. You squash a few, they keep coming. It's very parallel. All the agents are making decisions independently, and it's when their interaction that basically forms the overall behavior. And they are also extremely adaptable. So you can take a group of agents, move them in an environment which is, if it's not extremely different, the collective will still thrive. So taking inspiration from swarm intelligence, from natural swarm intelligence, we want to generate something that uses artificial swarm intelligence. And that's where we actually try to work. So we put together swarm intelligence and collective robotics, and we have what we call swarm robotics. And it has a few governing principles that we want to use into designing our systems. The governing principles for swarm robotics are, you're probably familiar with them, decentralized control. So every robot makes its own decisions. We have no predefined leaders or roles. Note that they say predefined because you can have specialization. And all the behaviors are based on simple local interaction. Now, when we put everything together and we have designed a system which is artificial swarm intelligence, and we apply it to a bunch of robots, our vision is to have something like this. We have exploration with many robots on Mars or other planets, and accomplish tasks that would be impossible for a single robot in the amount of time. Clearly, this is Photoshop, but this is our goal. Now, looking at this, you might say, well, I've seen this before, right? I mean, looks familiar, right? We have drone shows. We have hundreds or thousands of drones flying coordinated behaviors. So why are you bothering with this activity? Well, if you look at drone shows, they don't really follow our governing principles. First of all, the decentralized control. No, they use a centralized planner. All the activities are decided in advance. We have a planner that makes the decision for every single trajectory. No leaders. We have a base station that orchestrates the entire show. So again, not something we can have on Mars or the moon. No predefined roles. Again, all the activity is scripted, so each robot has its own role and cannot be changed, which is bad if you want to have a very fault-tolerant system. I recently assisted the drone show at IROS in Abu Dhabi, and I saw drones falling out of the sky. The show more or less worked, but there were a few that just dropped. And it's not like the show adapted to this. They just had holes in their show. And the last one is simple local interactions. Local meaning that each agent interacts only with its neighbors. And as far as I know, we don't have GPS yet on Mars. So we cannot have what they have. They don't rely on local interactions. They have a global positioning system. So we're not there yet to have the system that can work with many robots, self-organizing, and providing the exploration. So I'll start with actually the most important part for field swarm robotics. So how do we make this swarm robotics a reality? Now, if you look at in literature, most of the swarm robotics research happens in laboratories. You are in a lab, you're in a controlled environment, you have small robots, you have the Timios, you have the Kilobot, you have robots that can fit on a table. And if you take them and you put them outside and it's raining, they're toast. Well, even if you put them outside, they don't do anything useful. So how do we make this into something that we can use outside in an unknown environment, possibly thousands of kilometers away? So there are many challenges. Actually, this lecture is supposedly called Challenges and Opportunities. It's mostly challenges because unfortunately life is hard. So one of the main challenges we have is communication. Communication is probably the key point, one of the key points, I would say, of having collecting behavior. If the robots cannot communicate, it's hard to reach consensus and make them agree on something. Communication doesn't have to be direct. Like you can have communication by your behavior or just, you know, with body language or just having mental models of what the other agent is going to do, but you still need some form of information exchange. And one in particular problem that we have is reaching consensus. So agreeing on who does what, for example, or agreeing on the next course of action, or agreeing on some measurements, or even some understanding on the environment. And if you have a situation like this, you have robots that are shaped in two clusters, and the green lines represents the links, so the communication links. If you have two clusters that are completely separate, they cannot communicate. These two clusters cannot, if they don't see each other, they cannot collaborate. And unless they have an assumption of what the other cluster is going to do. And what happens to their belief state when these two clusters get together? So all this information exchange, it needs to be studied, and it's one of the challenges we have. The second challenge is perception. Perception means understanding the environment, perceiving what it is. This is still an open problem in robotics. We have to define the representation. Sometimes if you work in an office environment, in the lab, you might need just a 2D map. Sometimes you need 3D, and the level of details that you need differs. Nowadays, we have something called 3D scene graphs, where you actually do clustering and hierarchical representations of environments. How do we do this, and how we make sure that all the robots in the swarm have the same understanding of the environment, at least to the point where we can achieve our mission? What type of information we exchange? How do we make them communicate? All this is an open research challenge. Coordination is another issue. How do we make the robots work together? They have to transport something, for example. They have to assign tasks. They have to decide where to go. All this requires communication, requires perception, and once you have communication and perception, you can provide some form of coordination. The example I have here, you have 4 robots. They have to find a radiation source. How do we organize the exploration? Who goes where? They have to decide among themselves, because we don't have a centralized entity providing this information. And finally, something that is mostly neglected, I think, if you want to go to the field, you need operations. Operations are boring, generally, because it's just sitting down and defining procedures and ways in which you can have robots perform realistically. So imagine that you have to do a field mission. You have to have a truck to transport your robots. You need to have a way to set them up when you get there. you need to have power, you need to have communication, etc. All these type of operations are necessary for realistic deployments, and it's something we work on. One of the things we do, for example, the most interesting types of operation is the interfaces and how we can present the information to the operators. So let's start with communication. We've done quite a bit of work on communication because whenever you go in the field, if you don't have communication, you might lose your robots. So the first thing we tried to work on was defining a flexible network architecture. And there's a lot of work in the communication community, in the telecommunication. And what we did was simply adapting it to the robots that we have. So this diagram might seem daunting, but it's actually not that complicated. Our robots fundamentally are provided with an antenna. And this antenna provides wireless architecture, wireless communication. Normally, what you do in a lab, you have your Wi-Fi. If you're outside, we're all used to have our cell phones. And we forget what infrastructure is needed to have our cell phones and our communication. So we have repeaters, we have routers, we have lots of infrastructure. We don't have this on another planet. Or even if you go in Northern Canada, for example, there's nothing there. So without this communication, we have to form our own network. So we use something called ad hoc networks. And in particular, we use mesh networks. I don't bother you with the standards, but 802.11s is a popular standard for mesh networks. We just use it. We have multiple antennas. We have 2.45 gigahertz and 800 megahertz. And all these interfaces works at different distances with different bandwidths. So we use something called Batman Advanced, which you don't know probably, but it's already in your Linux kernel. If you have any machine with a Linux kernel that is recent, will have already this module. And this module fundamentally sends automatically discovery packets and discovers other nodes that are nearby and creates a mesh network that adapts in real time. So just by reusing this, we can have a stable network that adapts to the movement of the robots. So we just had to play a little bit with the parameters, and we can bond different interfaces. So we can have communication happens at high speed when you're in close distance at 5 gigahertz. And when you're far away, kilometers, you can still have communication with 800 megahertz at kilobits per second. So you can provide telemetry on one channel and images, for example, in another. And all this is fully adaptable. We have that each robot, for our own purposes, projects a wireless signal, so we can connect with our computers just for debugging. And then we have, if you have a ground station, for example, for experiments, you can have a cell phone connection to somewhere else. An example that we've done, we did an experiment at the Canadian Space Agency Marciard, where we had the robots forming their own networks and communicating. And we had a ground station providing an LTE connection, so cell phone connection, to the actual control room, which was 15 kilometers away. So we could actually simulate the same delay that we have with the moon, with our ground operations and the robots. And the people in the ground operation room couldn't see the robots. They were 15 kilometers away. So it was a good simulation of controlling robots on the moon. Now, as you know, we have to design interface and choose interface so that we have the proper throughput and latency. Now, I'm sure here nobody's very interested in, particularly interested, let's say, in wireless signals, but the main takeaway of this figure is that as the distance grows, communication becomes spotty. And this is what you expect. And in fact, you have to design your network in such a way that is tolerant to this frequent disconnections. You have here, as the distance goes to the maximum, you have that the robots disconnect, the latency increases, and then the throughput goes to 0. So In fact, that's what we did. We have we based everything on a publish subscribe paradigm. So you can register to some topics and send information on the topics, just like Ross. And we have best effort communication. So sometimes the packets are lost, but then when you reconnect, you can regain the information. The result is that we have a stable network. We can go out in the field, put all our robots, the robots form their network, and we can just open our laptops, and it's like having a Wi-Fi in the lab. The result is empowering once you are outside, and you have a robot that is a few kilometers away, and you can still control it, and you can still see the telemetry. So this is one of the things that we had to do first to have practical multi-robot systems in. However, research is still ongoing because, especially concerning perception, we noticed that if you don't constrain information exchange by the robots are generating maps, are collecting information, and the throughput that they need just to exchange the information as they collect more and more, it grows. And it grows, as you see, almost exponentially. Actually, in fact, it is exponentially. So without any constraint, longer-term deployments become unfeasible because the communication requirements increase with time. We don't have yet a solution for this. We have ideas that I will tell you later with in the perception part. But the problem is that communication is still an issue and needs to be worked on. Another point we have in communication is that we need an operator. Why do we need an operator? People say, oh, your system is autonomous, you shouldn't need an operator. Well, the thing is that if you take a bunch of robots and you send them to Mars and you never talk to them again, basically you wasted a lot of money. You could have just took them and dumped them in the bottom of the ocean. It would have been the same because you never see what they're doing. So you need, whenever you have a realistic mission, you need to relay back the information to the operator. This can be done with an intermittent link. So the robot gets out of communication range and comes back. This is what happens regularly with robots on Mars. Sometimes the relay satellite is not in communication range, so you don't get to talk to them. Or you can have an end-to-end link, which is maintained constantly. Generally, we thought that one of the most important things to have is one of these end-to-end links. The reason is that it has a lot of applications on Earth as well as on other planets. On Earth, imagine that you are looking for people in the water and you have a swarm of drones that are looking for people that are lost in the ocean. Distances are very large, and you can have intermittent communication, sure. But once you found the target, you want to establish a communication chain so that you have video feed, for example, for the first responders to see what is going on in the water. If it's actually a person, is it alive, is it not alive, etc. For the Moon and Mars, you're exploring a cave. You want to have a rover on the outside and smaller robots inside the cave exploring that form a communication chain so that you can relay the information back to the outside rover, which will have an antenna to send information back to Earth. So we defined something we called swarm relays. We had role-specific behavior where we have a bunch of robots. We have a worker robot that tries to go towards a target. And as its communication link degrades, it calls for other robots to intervene and access networkers. So you have, at the beginning, you have everybody's free. They don't have a particular role. A worker starts to go towards a target. And as it moves, it calls the free robots. They become networkers and form a chain. And this chain, this link, provides an end-to-end link between the target and the route or the base station. This can be seen here that we did with multiple targets. You have a bunch of robots. They form this sort of tentacles. that expand towards the targets. We did the experiments in the lab where we had multiple types of robots, flying, not flying, and we had networkers and workers. We worked with and without obstacles. Now, we don't see here the obstacles, but if you have obstacles, you can do path planning and go around the obstacles. And if you have, in this case, you can also have heterogeneous swarms where you have that the robots that can go through this hole are just the flying robots. And so if your path planner tells you that you can only go in 3D, you can decide which one is the worker and which one is not. So far, still in the lab, not yet in the field, but we'll get there in a second. Another option that we had for communication was to, instead of using robots to provide communication relays, to have fixed relays. And this is dropping communication nodes. So this was some work that we've done for the DARPA Subterranean Challenge, which is a field robotics mission where you have to explore caves. And we had that the robots would establish a communication sort of prediction. So they would monitor the signal quality in every point. They would do prediction of the signal to noise ratio and try to figure out the best place to drop these communication nodes, because the number of communication nodes we can drop is limited. So in the end, we had these robots. We had Spot that was carrying, if I remember correctly, 6 COM nodes. We had each robot was carrying about 6 COM nodes. And as they were exploring, they were dropping these nodes that would provide relays, and you could expand slowly your exploration of the caves. And the idea is that you can disconnect. You don't want to be always in connectivity. You drop the communication node, you collect some data, and then you go back to in range of the communication nodes to download the data toward the ground station. One last thing I want to mention about communication. Sometimes it's very difficult to transfer large amounts of information, especially if you are in a cave. If you are in a cave, even if you have these COM nodes, you might have low bandwidth because of reflection, multipath, metal presence, magnetic minerals, who knows. The idea is that generally when you go in caves, your expectation for communication range and bandwidth are low. So one thing that you can do, if you cannot transfer your data, you can carry it. And this is something that, there was an old saying is like, do not underestimate the throughput of carrying a 4 terabytes SSD to the other side of the country, because sometimes it can be faster. And so we had this idea of using something called data mules. So we have imagine that you have a capturer that generating data, and you want to bring data to a processor. We can have these networkers that physically take the data, go close to the information, they transfer at high bandwidth, and then they physically carry it to the processor. And that was actually a very fun project. We did, again, experimented in the lab. And basically, the data gets split into datagrams. The datagrams are given to different robots, and the robots physically move close to the processor. So in this case, we had images that we collected, and we carried the data to a processor that was doing some image recognition on said pictures. So you can, it's a bit dark, unfortunately, but what we had was that we have objects around the arena, and the objects were apple, bottle, and we have some robots that had a GPU installed, and some other robots that most of the robots didn't. And the GPU was running YOLO. We were carrying the images, bringing that to them, and they could do the processing. Again, we tested this in the lab, and we also put it in the field. Yeah.
Can we ask a question?
Yeah, sure, anytime.
Okay. So my question was, how do you assign the roles here, or are they predefined?
No, well, in the case of the data mules, they are based on the characteristics of the robots, so they are predefined because the processor is the one with the computer. There's nothing you can do about it. The data mules are the ones with large space to carry data. In the one before, they were assigned dynamically in the swarm relays. Now, these are some of the challenges in communication. Now let's move on to perception. Perception is probably one of the most difficult things in robotics. Just figuring out what it is around you is we humans do it very easily. It's easy for us, but it's very hard for the robots. And to understand perception, we have to actually open up a bit the autonomy and perception stack that we have in our robots and look inside to better understand what the challenges are. So first of all, we have a bunch of sensors. Robots have a bunch of sensors, and they collect these sensors, the information from these sensors, and they put them together in a perception stack. As today, I was reminded as well, we have that action and perception are fundamentally interrelated. So our perception and mapping has to be actionable in the sense that whatever representation we have of the environment, we have to be able to use it to do planning and control and action. And these two things are connected. So we can actually have what we call active perception, where we move specifically to have a different perception of the environment. So in this case, we have in our perception and mapping stack, we collect different sensors, LiDAR, visual, inertial. We construct a mesh of the environment, do 3D, and we put together a 3D map. We consider elevation, we consider inclination, we consider traversability analysis, and a bunch of other things. These representations generate fundamentally maps and pose estimates that we use to perform planning. Planning means we do planning both for locally, so how to move in the local environment to avoid dangerous or dangerous things or obstacles. So we do traversability analysis, we try to avoid holes, we try to avoid too steep slopes, etc. And we also do global planning. Imagine that you have one robot. This is difficult for one robot. It becomes more difficult for multiple robots. So when you have to do global planning, means that your robots start at the entrance of a cave and they have to decide where to go. So they do share information about what they've seen, and they decide who is doing what and which part they have to explore. And this goes together with mission planning, which is when you have a specific mission, could be anything, you need to have a certain number of behaviors that you want to implement. Imagine that you have to do prospecting on the moon. You need to be doing drilling, you need to be doing scooping, sorting of regolith, for example, collection. All these things have to be scheduled and assigned to different robots. And as you go down the stack, you have finally control and actuation. So once you have decided what to do, you can do motor control, arm actuation, and you have to integrate this with the communication we described before. So we have the mesh network management, exchange of information of belief, and you have to provide enough information to a ground station to have proper situational awareness, especially for the operator. So here you see an example. Here we had one of our robots that was doing, actually I'll show you the mouse, was doing a scan of a rock. And we had a microscope installed at the top of the arm that was used by the geologist to look at the grain of the rock. And so we do a 3D scan of the rock, and then we can use a simple point and click interface to decide where to put the arm so that the microscope can provide the picture to the geologist. So, as part of this autonomy stack, we defined Swarm SLAM, which is a simultaneous localization and mapping system for multi-robot systems. It's a distributed rendezvous-based SLAM. What does it mean? First of all, are you familiar with SLAM? Okay, good. So the idea of simultaneous localization and mapping means that you are detecting your environment and figuring out where you are in it at the same time. And rendezvous-based means that the robots might do their own thing, but when they get together, when they get in communication range, then they exchange information, trying to figure out if they have seen the same places. And they use this information to do what we call post-graph optimization. So they look at the past poses of the robots. Poses means position plus orientation, and use the constraints generated by saying, okay, we two robots have seen the same thing. So this same thing has to be in the same place in the map as constraints in an optimization problem to fix the maps and avoid any form of drift. This is connected with neighbor management because we have to figure out when do we get in communication range. And again, with all the network infrastructure I presented before. So now you've seen a lot of robots, pictures of robots. Now, I haven't told you exactly what robots we are using, but generally we have all kinds of robots. In this case, what you see here is how the maps change as the drift gets removed by the robots. These are trajectories. The different colors represent different robots. And we do it, one is just showing you the pose graph, so the series of positions of the robots, and the other one, the map. And as you can see, the maps are generated by different robots, and then they are fused together, and the orientation and translation is fixed based on these mutual constraints. And you can actually have global maps that have very low error using this system. Yes?
Are the maps then generally better than if we would just do SLAM on one robot, or is it just faster to build up a larger map?
You can, basically the quality is about the same. It's faster because you can do multiple sessions at the same time. If you have one robot to fix, you can do the same thing, post-graph optimization, but you have to do loops. Okay. So instead of having, we call them intra and inter-robot loop closures. So you have to, if you have your robot that performs a loop closure, you can fix your map. If you don't have loops, but you have inter-robot loop closures, so between robots, then you can still fix your maps. Ideally, you want a bit of both to have the best results. So you want loop closures and other loop closures so that everything removes the drift. Yes.
One of the real world challenges with these kinds of robots, whether it be in cave, search and rescue, or the military, is the environment can change very quickly.
Yes.
And how are the robots deciding that, oh, I've been here, and you've been here, but it was different when you were here than?
Yes, this is actually quite a hot topic, and in research is including time in SLAM. There's quite some work from there are a few groups working on it. One of the most famous, I guess, is Luca Carlone from MIT. They've done Chronos, which fundamentally detects if there are new objects or the geometry has changed over time. The problem is their approach is very memory intensive, and I don't think it's very practical in the end, because the amount of memory requirements increase exponentially with time. So if you go above, I don't know, a few minutes, you have really exploding memory requirements. There's also other work by Liam Paul, where they try to figure out probability distribution for changes in environment. So there is some work. The idea is that this is quite a hot topic of research. We have some work to remove dynamic objects. I'm not presenting it today, but we do have some work in that direction. So quick intermission. I show you a lot of robots, and I want to show you that how we started and how we're going, because maybe you get a better feel of what we're doing. We started with these robots, these guys, which are not field robots. These are cameras. They are terrible robots. They are slow, they are stupid, and they tend to get, if you get even a little bit of dust in their wheels, they get stuck. So not my favorite robots. Then we decided, okay, these robots are not really great. We still use them in the lab sometimes, but they are not really well working. So we built our own drones. We call the Cognifly. It's a flexible robot, so you can take it, squeeze it, and throw it on the wall. It bounces off, and it's fundamentally supposed to be indestructible. And they even use it for a course. And I discovered that it's not as indestructible. When you give it to undergrads, they manage to destroy them anyway, and fly them into walls, people, fire extinguishing equipment. So in the end, I decided to stop using the robots, and we went back to the good old cameras. But we gave them a hat and a lot more computing power. We added LiDAR cameras. Still, it's like lipstick on a pig. So it's terrible robot. We added a lot of stuff on top. And finally, I decided, okay, I give up. We need to buy better robots. And we went and bought a few of these guys. These guys are the Robotics. They were supposed to be great. They might be even worse than the cameras. I took these robots on field missions. They told me, oh yes, the IP64, they're very, very tolerant. I don't know what monkey designed the transmission system of these robots. Sand gets into it, and it's made of plastic pins. This boggles the mind, but you have the transmission of your robots. To avoid overcurrent, what do? You put a current limiter. You just, temperature sensor, do whatever you want. No, they have a mechanical system where you have plastic pins that if there's too much torque, the plastic pins break, and then you have no more torque. But then you have to remove the entire transmission system and change the plastic pins. This robot got stuck in the sand, broke all the pins, and we did say, well, it doesn't work anymore. How is it possible? We called the company and said, oh yes, it's our safety system. Excellent design. So in the end, we stopped using these robots as well. By the way, this arm that you see is a Kinova Gen 3 Lite, another arm that we thought it was a good idea because it was cheap. Terrible idea. So this is a fun part of this presentation. So you see this thing is an instrument that was made by a company called SpaceClick, and it's a spectrometer and a microscope and a 3D camera all integrated in one that we used with the European Space Agency to do prospecting for the moon. The arm was supposed to have a payload of 500 grams. I told the company said, sure, no problem. Guess what's the weight of the PRP? This instrument is 600 grams. I said 600 grams, 500 grams, probably would work. It doesn't. So what happened is the arm overheated and released everything and smashed the instrument on the floor. So again, field robotics had stuff. So we went and bought new stuff. So we have the Scout Mini is one of this actually is a good robot, works very well, had no problems whatsoever. Very tolerant, works with excellent control and good suspension system, tolerant to rain, dust, etc. And we went for a bigger robot for this one, the Scout, which is by itself, I think the overall platform is about 90 kilos, so it's a big robot with a robotic arm, LiDAR and everything. And this one is going happily in the sand, mud, grass, snow. It works very well. Okay, this is just a quick intermission to show how the robots have changed. We also now have quadrupeds, we have Spot, we have the Unitree ones, etc. Now, we have seen coordination, we have perception, we have seen communication. Now we have an idea of what the environment is. We can communicate. How do we coordinate these robots to do things? So that's going back to our autonomy components. We have the planning. And I want to focus in particular to the global and mission planning, and a little bit on global planning, local planning. So fundamentally, for global planning, what do? We need to explore. This is one of the main missions we have. We have to go inside caves, see what's there, look for signs of life, for example, or other interesting things. The main target that we have is to maximize what we call the exploration game, which meaning we want to maximize the amount of information that our robots are collecting collectively. So this is the only math I have. It's not really math, but it's just a problem definition. So if you have an area that you want to explore in space, and you have a certain number of sensor field of view parameters, you can compute a set of viewpoints that you want to see that can classify the environment into free space and occupied space by objects. So this is our an initial definition of our problem. Now, what we want to do is we want to maximize the amount of information we get with this set of viewpoints. The viewpoints have to be in free space because the robots cannot go inside obstacles. And what we want to get, we want to maximize the number of voxels that we can collect with all the robots. There are lots of methods that have been presented in literature. There's graph-based planning. I don't know if you're familiar. Basically, you represent the environment as a graph. You generate this graph randomly, and then you prune it and you figure out which is the best graph for the exploration. There's viewpoint-based planning. So GP Planner 2 was made by Kostas Alexis Group in Norway. Viewpoint-based is Stair Planner from CMU. Then we have the cost-based exploration planning made by NASA JPL and MIT. We have next best view planning, motion primitive, and there are so many. The common approach, however, is to define a local environment, then you do exploration, and but you keep track somehow of the global exploration from all the robots. Local state exploration means fundamentally sampling from states in Q3 and building a graph that connects these nodes so that the robots can follow a trajectory. And then you evaluate this graph with this volumetric gain, so how many boxes you can connect given the field of view of your sensors, and then you choose the path with the maximum exploration gain. You have to do this in real time, so it has to be fast as well. So you see here, for example, we have a bunch of possible trajectories, a bunch of points that we have sampled that are in free space, and we try to figure out which one is the most effective. Okay, this I lied. This is the only math that there is, but fundamentally, your exploration gain has to consider the volumetric gain, and you also consider two other factors. The distance penalty, so you want to, since you shouldn't trust too much points that are too far away because your knowledge and your uncertainty grows, you try to minimize the trust that you have in far points. And very important, a direction penalty. You don't want your robot to keep going back and forth and changing directions because that's inefficient in terms of energy. So we have this distance penalty, the direction penalty that tries to make the robot go as much as possible in the same direction. This is also useful when you have multiple robots because then you can send them in different directions and they keep going in that direction. Yeah, so it's a little animation. You see the robot is exploring. This is a single robot. Is performing the exploration. You see the path is selected and it forms this nice exploration. This is the exploration in a simulated cave. The problem with this approach, which explores the local space, is that you can end up in dead ends. You have intersections that you don't know what to do. You have repositioning when you have low gain. It's hard to do, and it's hard to coordinate with neighboring robots when you're only looking at the local space. So to overcome this, normally people add a global exploration graph that is actually what is shared between the robots. So you maintain a sparse global graph of all the explored parts, you maintain a connected set of the frontiers of what has been explored. And whenever the robots get together, they exchange the information. So they exchange their frontiers so they can have a sort of a global view of what has been explored, what has not been explored, and they can coordinate easily in this way, just using their own internal algorithm. By providing the information of what the other robots have seen, I can decide what's best for me, and I don't have to rely on a centralized planner. So this is for fundamental distributed optimization that sends us in the maximized exploration gain. This enables us to do repositioning at dead ends. So whenever you have a dead end, you can use the information of the global path to go back and try another path. Also the same thing when exploration gain is very low, you can just go backtrack on your graph and figure out another path. You can do homing, so go back to the initial position because you have the full graph, just following the global exploration plan. Excuse me. And this also is a compact representation of what the other robots have explored. So exchanging this minimizes the bandwidth and allows us to take these graphs, fuse them together, and provide a global graph for the exploration of the whole swarm. We did implement this, and if you want, you can actually download it right away. It's MGG Planner. It's just it was just accepted on RAL before Christmas, so it should be out now. I don't know exactly the page and number, but you can find it probably on the internet. And we did test on the field with multiple robots at the Canadian Space Agency Mars Yard. And we show that fundamentally we get good exploration gain, and we get also very short runtime. So MGG fundamentally uses a local exploration planner based on the grid. So you can do very fast scan because you don't have to generate many graphs. You have a grid, you explore the grid very, very quickly. And then you have a graph for the global exploration, which minimizes the bandwidth. Basically, we put together TER planner and GB planner 2, and the result is something that beats both. So we did some tests as in the field using the communication infrastructure I mentioned, the perception stack I mentioned, and the results are that the robots were exploring. The Mars Yard is a terrain of about, I think, 70 by 150 meters. And we had, in this case, we had 3 robots that were performing the exploration. And here you see them going around happily and generating a map and providing this map to the ground station. They disconnect, they reconnect, and it's for the operator, this is actually fairly easy to use.
So is this only being used with ground-based vehicles, or are you doing it with aerial?
We use the aerial for this particular tests. We use the ground-based vehicles, but we do use aerial vehicles as well. It's the same. The planner is full 3D, so you can use it with whatever.
Even in confined spaces like cave exploration?
Yeah. We have I have an example later for cave exploration with a drone. So. Okay, this is another thing that we need to do is mission planning. Mission planning is maybe a bit more boring, but sometimes you have to define what the robots have to do, and the best way we found is to use behavior trees. Behavior trees is something that's used a lot in video games, and fundamentally you have decision points, and based on you start from the tree, and you fundamentally decide which behavior to implement based on a series of conditions. And behaviors are exploration, acting as relays, finding to rendezvous point, to communicate, to exchange information, active slam, or even energy sufficiency. So, for example, another behavior points is when do you return to a charging station when you're running out of batteries? And this, in fact, is a particularly interesting thing because if you want to have a realistic deployment of a robot, we need to have energy sufficiency. Because the robots, the endurance of the robots is clearly limited by their batteries, and especially if you want to explore caves on the moon or Mars, you don't have any way of charging yourself because there's no sun. Unless you bring a radiothermal generator on each robot, which is not feasible because it's too heavy and expensive to put many. RTG is like the nuclear batteries used by Curiosity and Perseverance, for example. You can use them for one robot, and they are very, very expensive. So we can't imagine to have 10 lying around. So we have this idea of if you go, for example, in a lava tube, you have a skylight. You can have you can drop the robots in the skylight. Gravity on the moon is not that bad, so they can even fall many meters without being destroyed. And a rover outside can drop a tether with induction charging, with wireless charging, and the robots can just get close to this charging station when they need power. When do we do this? We need to coordinate in such a way that we don't run out of batteries ever, because otherwise the robot is lost and the mission still gets accomplished. So we defined this, we control barrier functions. This is for a single robot, and we extended this for a multi-robot as well. So fundamentally, what we have is that the robot does its own mission. You don't have to worry about the energy. There's a second controller that acts as a sort of filter. When the robot gets dangerously close to running out of batteries, the second controller takes over and basically drags the robot back to the charging station. And this is completely transparent from the mission. This works by keeping track of the path that you did to go away from the charging station. And based on this path, you can compute the energy requirements. The path can go up slopes, so the energy consumption changes depending on how slippery the terrain is, how hard it is to go, if there's wind, if you're using drones, for example. You can all consider this. And then whenever the model says you would run out of batteries, you get dragged back and you arrive at your charging station exactly at the energy target that you set. Clearly, it's never zero because it's risky, but let's say you arrive at your charging station always at the 20% level of charge. We did this as well when sharing a charging station. So here in this video, you see that you have a red circle in the middle that represents the charging station. And the robots are going inside the charging station to recharge, and they coordinate in such a way that no robot runs out of charge. To do this, we had to define another type of control barrier function that is called the coordination control barrier function, that lets the robots exchange information about the battery levels and schedule their comings and goings to the charging station. At the beginning, if the robot starts all at 100% batteries, you will not have 100% utilization because the robots, they cannot use all their batteries and go back together. But eventually, over time, they will distribute in such a way that you have the maximum utilization possible of the battery. And this ensures coordination. The only limitation of this approach is that the robots have to be able to know and communicate with all the other robots. They can have this connection, obviously, but generally, they have to add information about the battery state of the others in order to properly schedule. Now, this is one example of coordination. One thing we worked on a lot recently is how to coordinate robots when you have heterogeneous swarms. So if you ask a group of people to stay in a room, you put them in a room and you say, okay, you stay at about 2 meters from every other person. What will happen is that if this gives an instruction, the people will distribute themselves in just about like this. The robots are oscillating a bit because of some noise, but fundamentally people will stop when they are at 2 meters from each other. If you take just a couple more people and you tell them your objective is to move from one part of the room to another, just by their movement, and the other humans following this instruction, you're able to steer the entire swarm. This is a shepherding example that we had before. So if you add leaders to the group, what happens is that the robots that are aware of the target mission, they can shepherd the entire swarm to another destination. So we can use this concept to perform a lot of interesting activities. And in particular, we can create heterogeneous swarms. We can have leaders that are carrying around a bunch of other robots that can perform a mission, but they are not necessarily aware of the entire complexities of the mission. The idea comes from the fact that we have a variety of robots available on the market. If you look at robots that we can find in swarm robotics, they start with the kilobots, the Keperas, and then you go up to more complex robot like the Spot or the Atlas or whatever other humanoid you can imagine. And these simple robots are very cheap, but they have very limited capabilities, while the robots on the other end are can do perception, can do planning, etc. So if you want to use a lot of spots, you can, but it's extremely expensive. And if you want to, if you don't have the money and you want to use a lot of Keperas, well, I guess you can, but the robot level behavior design becomes very difficult because they don't have the intelligence, and you have to figure out really emergent behavior. You have to do a lot of trial and error, a lot of training to make the robots do what you want to do. So the idea is that we can put these things together, have a few intelligent, capable robots and many less capable robots to perform a task. And you can use swarm level behaviors and guide them with these leaders. And this allows you to basically solve the global to local problem where you have what you want the swarm to do and what you want the little ones, the swarm elements to do. How do you put these two together? You can have the global, the behavior of the swarm, which is emergent, and you can steer it around with the leaders. This allows us to do mission planning with hierarchical behaviors. Fundamentally, this is more, you know, still in wishful thinking, I would say, mode, but the idea is that we can take a bunch of elementary behaviors and combine them by using these leaders that push and change the parameters of the system so that we get the top level behavior that we want. And basically, we have a way to unlock the full potential of heterogeneous swarms, behavior composition. I believe that this actually is what nature does fundamentally, because we have lots of examples of the type of hierarchical behaviors in nature. Homeostasis, for example, control the body temperature. You have the hypothalamus that is basically collecting information, making decisions, and providing the actuation. And you have, you have a bunch of neurons that work together, and you have specialized areas in the brain for specific things. So I think that this is actually the way to go to create this type of complex behavior. To prove this theory, these ideas, we designed an example mission where we wanted to have exactly this type of hierarchical behavior. So imagine that you have to do a nuclear disaster cleanup. You have a set of clever, smart, capable robots that are radiation sensitive. Electronics is generally more radiation sensitive, the more, if you use powerful electronics, generally they are more radiation sensitive. If you use radiation hardened electronics, they are less capable, but they can tolerate more radiation. So you have a few leaders that have to act quickly, figure out where the radiation target is, and then take a bunch of simpler, cleaner worker robots to do the actual cleanup. In this case, we have these robots that the guides that explore using the exploration algorithm I described before, try to find the radiation target. Once they find it, they go back homing. Remember, the global path planner allows us to go homing. They go back, they collect the robots using chain formation. Why did we see chain formation before? Swarm relays, the communication chain. So we have already the software to get the robots to go into a chain, take them to the radiation target, they perform the cleanup, and then while the guide robots go away and avoid being affected by radiation. Okay, there should be a video here. And my presentation is stuck. Work. Okay. Now let's try again. No. Okay, yes. So the idea is that in simulation here we have 2 guides with LiDAR and 10 workers, which is only fundamentally use proximity sensors. So you have since we don't want to waste time, we have the workers already are exploring, but they only have proximity sensors, so they just go randomly. And they use a bug algorithm, in fact, which is pseudo-random exploration algorithm. And while the 2 guides are exploring the map, and once they find the radiation target, they found the target. It was already found by 2 of the robots, but not enough to do the cleanup. So once they found the target, the robots go back and collect the robots, form the chain, and take it to the radiation target. Now, we did experiments in simulation in different types of environment, urban, maze, forest. We tried with different number of robots, and fundamentally, we can show that the percentage of mission success, fundamentally, if you use a hierarchical system, is consistently 100%. If you just go for robots doing bug algorithms, so completely egalitarian, so no leaders, the mission success decreases as the number of robots that have to reach the targets increases. So suppose that to do the cleanup, you need 10 robots, then the probability of success decreases very quickly with the more complex environments if you don't have leaders. We also show that the cost of the swarm decreases significantly if you have guides, even if their guides cost 3 times as much as one of the workers. So fundamentally, this is a winning proposition. I had another video, but oh no, I was here. Sorry, because I had no. Okay, I forgot to put it. Never mind. We also did the experiment in reality, and I forgot to put the video. So sorry. But the idea is that yeah, you can see the same thing in reality. I want to conclude the coordination with something about coordinated behaviors, where we have, for example, collective transport. And you can, just by reusing the same things I described, have collective transport. You can have rotations, movement of objects of different weights. And we can have something that I find particularly amusing, is something we call smart particle swarms. Smart particle swarms is when you have a group of leaders or shepherds that want to lead a bunch of sheep, but the sheep use only simple local interaction rules. But the interesting thing is that you can use the shepherds not only to push the sheep around with the same rules. So the idea is that in this case, we have the shepherds that go around the sheep. They can only detect the sheep, so they don't know how many they have. So they go around and detect the shape, the size of the flock, and then they can shape it by moving around and then transporting it. But what if you can change the rules of the shape? So imagine that your guide can provide a sort of propagation of information. So it can broadcast new parameters for the sheep. And you can tell the sheep to change their field of view, their density, so how much they react to their neighbors, how much to react to the shepherds, if they should try to keep the same orientation, so basically they locked into a shape, or they can be loose. This is changing the rules of the game. So you can have really complex behaviors because your leaders during flocking can actually change the rules of the game and have a sort of combine multiple behaviors for the sheep. The result is that you can shape in anything, things like you've seen before here. In this example, you have that the leaders, the shepherds go around, the sheep are just minding their own business. Now they are around, and you will see that something happens. They change the rules because they wanted to get in and then push them around. So they change the rules of the sheep. Okay. The last part is operation. And how do we do this? Once we have coordination, we have perception, we have communication, how do you actually operate these things? How do we get situational awareness from a large number of robots? How effortful it is to control a swarm? These are all things that we try to answer in a few works that we've done, mostly with NASA JPL and in collaboration with Professor Coffey from Concordia University, which just happens to be my wife, but that's the detail. Where that your expertise is actually biosignals to monitor cognitive load. So we defined, we went into caves with a group of spots, and we defined a user interface to schedule operator activities to make situational awareness and simplify the life of the operator. What you see here is a picture of the interface that we used for the DARPA Subterranean Challenge, where we had 8 robots, if I remember correctly. I can count them. But the drones are not shown here, but we also had drones. So we had also a couple of drones. And it looks like StarCraft. We discovered that basically StarCraft is probably one of the best interface you can have to control a multi-robot systems. We also tried with the VR interface. And we monitored biosignals just to figure out what was the level of involvement for the operator. We tried to use operators that were already skilled. We also did a user study with many people, but we tried with the European astronaut Matthias Maurer, and we measured pupillometry, skin conductance, heart rate variability, and there was and use also questionnaires, but I don't really trust self-reported difficulty. So here we calibrated fundamentally pupillometer with the NBAC task, which is a task to measure provide a baseline for the cognitive load. Then we end user and field studies. So we had a VR interface, and which is, I have some trouble. Okay, videos today. We had a user study with 30 users where they use both a StarCraft-like interface and virtual reality. We did the tests in the caves in the wild, and we had this VR interface just to see if having the immersion and using the spatial perception capabilities of the humans could actually improve the operations of these robots. And so we had both the 2D and the VR interface, and we measure objective and subjective workload measures. The result is that field cognitive measurements are bloody hard to do. So if you are in a study in the lab, no problem. As soon as you go in the field, it's a mess. So here I put some pictures of our work in the caves of Mexico. This is one of the fun part of my job is that the field missions. So I like to go I have a couple of photos more of field missions, but the one in Mexico was particularly interesting because we were in the jungle in Mexico, far away from civilization. And by far away, I mean really far away. So we landed in Mexico City. We had to take a bus for 2 hours, then another bus for 2 hours, then 6 hours in the back of a pickup truck. And it was pouring rain. It was cold. It was on top of the mountains. And we were in the back of the pickup truck freezing with all our equipment in canoe bags. We arrived at the camp. The camp had no running water, no toilets, as you can imagine. We were living in the mud and with serious water shortage. We couldn't wash ourselves. We only had filtered water to drink from that we collected from the rain from bins. Great, great time. And you try to sleep. You want to sleep? No sleep for you, sir. Because at night, there were chickens, dogs, other things. It was a complete hullabaloo every night, and you try to sleep and it was impossible. This means that every cognitive measurement we take was done on people that were stressed, annoyed, lack of sleep, and they were also going inside caves. So you see there's pictures here. We put cameras on people to figure out what they were doing, and they're going down, they're going up, they have physical activity. Measuring biosignals is very, very difficult. Pupillometry becomes impossible. They move too much. There's too much changes of light. There's the very dark of the cave. Then you have the cone of the lamp. We found that the only things that actually works is heart rate variability, because with the camera we can discern when they are doing physically intense activities, and we can also ask the participants to provide in front of the camera numbers that represent their effort. So we can use this information to sort of discern and figure out their cognitive effort. And so fundamentally, we had this publication that came out recently, the feasibility of cognitive neuroscience data collection during speleological expeditions, where he had to use drones inside cave while performing cave exploration. And in the end, the result is yes, we can do it. It's difficult, but it can be done. Now, and one last thing I want to mention is the slides I added at the last minute is human. We also worked a bit on human robot and human swarm interaction, and clearly the LLMs, foundation models are all the rage nowadays, language models. So since we can interact with the robots with natural language, thanks to these models, why not mixing them with our exploration stack? And so we decided to make a demo for the Canadian Space Agency, showing this is the future where the astronauts, they have limited dexterity when they are on the moon because of the spacesuit, can interact with the robot. So we took really off-the-shelf models. We took Llama 3, WhisperNet, Baklava, and Piper, which are just, we can download them if you go online, and you can run them on Jetson Orin, and they run at real time on just a normal embedded card. And what happens is we get voice input, we have video input. Video input is transformed into a prompt. So in the description of what the robot is seeing, voice is transformed into a prompt via WhisperNet, basically text to speech, speech to text. We feed it to a large language model that generates either robot control or a prompt, a response that goes to Piper that does text to speech and voice output. And the result is something like this. Now, you can't hear the sound because I'm not connected to the sound anyway, but I can tell you what's happening. So what my student is telling the robot to stand up, and the robot stands up, is asking the robot to describe the environment, the robot is describing the environment. The best part you can do is it tells the robot to go and look for an object. And the robot is starting to look for an object. At that time, this is a unadulterated video, so it's not cut or anything. This is actually when the robot stops, it's because it's doing path planning. We hadn't optimized the path planner yet for Spot when he made this video, so you will see it will stop a couple of times to just do path planning. So here it's stopping, it's deciding where to do the exploration, maximize the exploration gain. There's a door here, but it's closed, so he thinks it's best to go through this door, and it goes through that door. Then looks around. The LiDAR is 360 degrees. It's trying to decide where to go. And it goes left or right. Based on the maximizing exploration gain, decides to go left, if I remember correctly. Yes. And it's going backwards just because Spot doesn't care. We have a 360-degree LiDAR. Problem is that we told it to find Baby Yoda. Baby Yoda, as you can see, we left it here. The camera is in the front. So the robot would be exploring anyway, but my student got impatient. The robot was exploring, was avoiding the obstacle. And they say, okay, show it to the robot. The robot stops, now sees the Baby Yoda, and says, oh, I found the Baby Yoda. And then goes back to the base. So now it's taking some time because it's doing the full path, the full homing path plan. So with a global path, and it starts going back. And we discovered doing this that Spot really doesn't like Baby Yoda. And you will see that why in about 10 seconds. See, it looks like it's avoiding it. See, it's avoiding, but no. and then it goes back. That's it. So now I have just a couple of pictures of field missions to conclude. We did a lot of field missions with the European Space Agency, with NASA JPL, NASA Ames, with Speleo Quebec in Mexico. One of my favorite missions was the one PANGAEA-X for Canadian Space, for the European Space Agency. We went on the island of Lanzarote. I don't know if you know where it is. It's here next to Africa. It belongs to Spain, and it's a volcanic island. And we went there with 10 flying robots. They were controlled by European astronaut Matthias Maurer. In this picture here, you see Matthias Maurer with the Spanish astronauts, and nobody remembers his name. Do you know the name of the Spanish astronaut? Me neither, sorry. But in the end, we had the robots flying. Clearly can't see much when they're flying because they basically look like dots in the sky. But the astronaut had a tablet. They could see the telemetry from the robots and control where the robots were going. The objective in this case was finding geological features of interest that would pop up as the robot found it, would pop up on the tablet with a picture. And the task was for the astronaut to find as many as he could in the environment. We did also experiments at the Canadian Space Agency, exploration of caves with drones, etc., etc. DARPA Subterranean Challenge, etc. Now, some open challenges that we still have is failure recovery, proper semantic understandings and knowledge representation for complex environments, and generalizable planners. What I'm showing you here is one thing we had was done by my student Vivek. See, the Spot is falling, it's slipping. This was during the DARPA Subterranean Challenge, and the recovery protocol was designed by my student. The idea is that we have the exploration planner is telling, go there, you can't pass through there. But the robot tries 2 times and keeps falling and failing. Eventually, it gives up and goes away. That's a perfectly reasonable behavior, but that needed to be coded because this is not something that we consider obvious. For example, the robot falls. You see now it's recovering automatically. This is done again by my student Vivek, but it's dangerous to recover automatically because it fell because it was an unexpected obstacle. It risked falling off a cliff. So here, based on the cognitive level of the operator, we can decide if they do automatic recovery. This makes sense if you have a time-limited mission. If you have search and rescue, you can't waste time. If the operator is otherwise engaged, it's better to risk, losing the robot than losing human life, for example. And instead, if you have a mission where you have time, you can just pause, stop there, and send a message to the operator. As a bonus slide to conclude is the dancing with swarms. Since we have coordinated behaviors, and we also have tiny robots that don't particularly cannot provide a lot of information, we thought, what if we can use the movements of the robot to convey information? And so we can have movements of the robots that are not directly related to a task, but convey attitude towards it. And my former student, former postdoc, David de Saint-Onge, carried on this research further by having a mission where you can have the robots, again, the jiggling on your screen if you are looking at them to tell you that they want attention or something like this to attract your attention. But what we did in this case was, let's make something artistic. So we strapped some accelerometers on dancers, and we defined a bunch of swarm behaviors that represent moods. How do we define moods? Well, apparently the dancers already have dance moods, but we let them decide which behavior represented which mood, and we classify their movements based on the training that we've done on the moods. And as we recognize a mood, we change the behavior of the robots. And so the dancer can have a choreography with the robots. And that's what's done in collaboration with the School of Dance of the UQAM, the Université du Québec à Montréal. That being said, I want to conclude saying the swarms are coming, and I would like to thank all my students and collaborators that helped me achieve all these things that we've done, discussed about. And I'm open for questions.